All right, we good? Yeah, great. So I hope everybody enjoyed lunch. So the next speaker is going to be Dave Maher, the Chief Technology Officer of Intertrust, who's one of the world experts in secure systems. Dave's been involved in all sorts of different research over the years. More recently, he's been working in new techniques for blockchain-based authentication. Today, he's going to be giving a talk on some of his more recent work, but starting with a walk through time over how we came to where we are today. Dave?
So I'm going to talk about history, but also want to bring a theme to it. And that theme is what drives innovation. And I'm not a big fan of the sort of like pure research, bringing a lot of smart people into a room or virtual room for that matter, and great things will happen. But rather that innovation really is driven by necessity. And in security, it's very often driven by survival, which is, I guess, a somewhat more intense form of that. So starting with World War II, which is where I was asked to start. We could have gone back all the way to prehistory, but in World War II, you may have heard of a couple of systems that were developed. Enigma, which predated World War II a little bit, and then another thing called system called Sig-Sally, which you may not have heard of, but I'll talk a little bit about. But both of these systems inspired immense advances in computation. In the case of Enigma, it was trying to break the Enigma code, and that spurred the development of digital computers. Digital computers as a concept were kind of well known, I guess, at the time, but as practice, totally different. Sig-Sally was a system that really drove the beginnings of digital communication, not just secure communication, but all of digital communication, and I'll explain how that worked. And then the next era in history, basically the Cold War era, spying was pretty intense, and it was actually becoming mechanized. And so the question was how do you respond to that? And so secure systems needed to scale, and that scaling of secure systems inspired even greater advances. And I'll go over a little bit of how that worked. Now we come to today, and we've heard today about how computing is ubiquitous and it's embedded everywhere and everything is hyperconnected, et cetera. And what we're seeing is that new computing models allowing for governance of data and device access are going to be needed, or in fact are needed, and to a certain extent are being applied now. But a lot of that came out of, a lot of the techniques to perform those actions actually came out of the 1990s development of digital rights management technology. So I'll go over a little bit of that as well. But generally, the theme follows this. Necessity and opportunity are sort of two sides of the same coin. Theory and practice bounce off of one another, and the requirements that you get out of necessity. And I think you'll be able to see how that worked here. So necessity in 1942 was declared by General George Marshall with a brief sentence that said, Roosevelt needs to talk securely with Churchill often and at a moment's notice. So they didn't want just a messaging system. They wanted a secure telephony system. The problem is that to be secure effectively, voice would have to be digitally encoded. The problem with that is that no one knew how to do that at all. There was no digital voice system in design, let alone in deployment. And digital transmission hadn't even been invented yet. There were no computers, no VLSI, no transistors. Yet, 16 months later, there was a secure telephone. It was a big, 40 racks, 50 tons, drew 30 kilowatts, but they made quite a few of these. And they were delivered worldwide, actually, to the Pacific as well as in the European theaters. It was highly secure, actually, because it encoded digital voice with a one-time pad, which many of you will know is a highly secure system. It's fascinating that the one-time pad code words, or code stream effectively, was recorded using modulation onto phonograph records. Phonograph records were physically carried to the ships and to the basement of, I think, Selfridges, which is where the UK version of this was, and other places around the planet. And then once they were used, they burned the records, effectively. But that system even had to be synchronized, of course, both sides, and this is a real-time system. Roosevelt or his staff members were actually talking to Churchill. So the remarkable thing was, yes, there was a thing called a vocoder, which was invented at Bell Labs in 1938, but it wasn't real time. So what a vocoder did was, it forms a model of your voice, basically a filter of your voice box, and an excitation model of what's exciting that voice box, and parameterizes that model, digitizes the parameters, and quantizes it, modulates it, sends it over to the other side of the channel after it's encrypted using those phonograph records, and then the other side, in real time, reverses the process. It synthesizes from the parameters that were sent. It's not like a lot of people think that you were just cutting up a waveform and quantizing. This was mathematical modeling of digital voice, of analog voice converted to digital. And that's why you had 40 racks of equipment, because there weren't any transistors around to do that with. Pulse code modulation was invented in the 30s, but it had no real implementation. They had to figure out within 16 months of how to make it work. And they did. You had the one-time pad, and people like Claude Shannon, who was quite young at the time, eventually published the mathematical theory of communication, which often is said to have been sort of came out of the thin air, practically, of his genius. I think it's reasonable to assume that his participation in the Sig-Sally project, along with Alan Turing and Nyquist and other great engineers, put a lot of questions in his mind about how to do that project better. So, like I said, there were amazing results in 16 months from a singular, unambiguous goal, very, very clear requirements. The team was aligned with the mission, organizational adrenaline, and just amazing things happened. And then there's a whole bunch of inventions that happened also during that period of time. There were slapped with secrecy orders, but I think they were published in 1976 as patent applications. Then came the Cold War. Communications remained principally analog. Long-distance telephony moved to analog microwave radio, which means theoretically anybody could listen to any conversation. New cellular radio systems were also analog, and the Soviets were spying, so what to do? Well, another call in this case came from Washington, and it said the president wants a secure terminal that looks like, feels like, and talks like a telephone. Sig-Sally was, an amazing achievement, but it sounded like shit. But the interesting aspect here is that they needed 1 million of these terminals because there's a lot of information that was being communicated around the world. And they needed to interoperate with everything, all kinds of things, planes, boats, conference systems, et cetera. And to help with the scaling, the people at the NSA said, we got this new non-secret encryption system, which was their terminology for public key cryptography, which was actually invented by the British. They said, check it out. We don't actually know how to deploy it, but you might find it useful. And you've got 2 years to do this, to come up with all of this. So we ended up producing, took a little bit longer than 2 years, but not much. And digital voice and data, again, was transmitted over analog networks. The voice coding algorithm, which sounded quite nice, is actually the same voice coding algorithm called code-excited linear predictive coding that is used today in all of your cell phones. There are improvements over time. But that came out of that requirement in 1981, and people wanted to have those kinds of improvements. And now, the key management for the million terminals did use public key crypto systems and a certificate authority. All of that was, again, developed in 1983. All of that eventually deployed commercially in the 1990s and 2000s with the onset of the internet. And then, of course, this kind of system moved to fully digital when commercial networks became digital. But this all predated the onset of digital networks. So let's, since I have a small amount of time right now, let's take a look at what is the survival issue that's driving secure communications and secure data systems today. You've got the hyperconnectivity, everything is driving, is connected. You've got cyber-physical integration. You've got scale and ubiquity of everything. You've got new interaction modes where all of the devices that have become computerized and have become networked are virtualized and put into a cloud and connected together there. So that, you know, the title of Bruce Schneier's book is, yeah, just press a button and up in the cloud all this stuff goes on and you can kill everybody. It's actually, there are just millions of ways you could do it. So it's kind of funny to laugh about it, but it's quite sobering. So the problem that we have right now is that a lot of the security systems that we have developed over the years are mostly for secure communications. And communications in, or secure communications in a system or a world where people actually want to talk with one another, want to interact in ways that we can't predict. And in fact, we can't even tell what is connected to what, because there are so many different connections being made. And so many different ephemeral networks are being set up with things like autonomous driving systems and just you with your perhaps medical devices walking into somebody else's house. Those medical devices are now at least 1 or 2 nodes away from some other network that you don't understand, and in fact, no one else understands. So securing things using traditional, VPN technology just isn't going to work. So the innovation is actually going to have to come from new computing models. And we know that Facebook, Google, Amazon, Apple have centralized control of your data, and applications or data are logically centralized. Yes, they have distributed databases and things of that sort, but from a control point of view, it's all centralized. And that is a big problem from the point of view of trying, again, to protect your data or your company's data, because the same is true, actually, to some extent, and is becoming increasingly true with corporate data. So there have been a couple of research projects that you may be aware of. Well, the Intertrust project we called the Personal Agent Project flipped the model, and now another project that has seen, at least over the past couple of months or so, some notice in the literature, which is Tim Berners-Lee's SOLID project. And the idea there is to separate data from function, which is kind of the opposite of what people tried to do in the 70s and 80s with object-oriented design, which was to merge the two. And then provide a way in which you can govern the data using rights management type technologies and make your data governable by you. Now, people don't want to do that because that's actually a lot of time and effort, et cetera. So you have to provide something, perhaps what we would call a personal agent or some agent kind of capability to deal with that. And agent technology is growing up. And I think this application will actually force agent technology to advance even faster. So the new computing model is this one here, where you see that a lot of data, whether it's corporate data or people's personal data, is at the lower level of the diagram in a protected data storage layer. It may be collecting a lot of data from the applications at the top, the app layer, which might be social networking and home management, insurance, et cetera, a lot of the things that we heard about today. So a lot of data may be fed into that, but you have under the independent, however, of those applications, you have the capability to import AI algorithms and other data processing capabilities to produce derived data, and then govern that derived data. And then when, for example, a social network wants data from you, the personal agent will help determine what information it needs, and only that information. So in an insurance application, as an example, one issue for a consumer might be compliance. Are you complying with speed limits or whatever? They don't need to know where you've been, all of the GPS data and all the other stuff that's actually become available. The idea here is that you only give, because you're in control, the information is necessary for that insurance compliance application to run. So this separation of functionality and data is at the heart of the SOLID project. And we'll also see that, that there are a number of other projects that introduce similar capabilities. I think the difference between what we have been looking at Intertrust and what the SOLID project does is so that we've realized that we're going to need to introduce an AI data processing layer to form the derived data, so you don't have to give it over to somebody else to do it, like Facebook or the insurance company or whoever it might be. Again, that's the idea of solving the problem of making data useful without having to actually divulge it. And this model will help do that. So I'm going to end with a little thought experiment. And here we know that the world is becoming hyper-connected, and bots are roaming all over the place. Mechanized computation is happening in places that we can't even imagine. And now they're being introduced into our bloodstreams even. We're starting to be surrounded by medical devices, but also they're actually going to be invading into us, hopefully with our permission. Trillions of sensors everywhere. And we've got all these new computational models. Networking is everywhere, et cetera. So the question is, in a few years, after all of this sort of gels up a bit, if space aliens encounter the Earth, what will they discern? And this is a different kind of survival thing. The Bruce Schneier says you've got one button you can press to kill everybody. This is a sort of like, what does the human race look like in 10, 20, maybe 40 years. And will it be, because of all that hyperconnectivity and centralization of control and power, would the aliens see basically a single organism, the human race as a single organism made up of human nodes, controlled by powerful special interests? Or will we implement some model like what I've been talking about, where you have individual people remain in real control of their digital identities? Thanks very much. I don't know if we have any time for questions, but I'll take one or two. Yeah.
With the introduction of digital music, digital supports like CDs in 1982,
Right.
which was the protection used at that time?
That's the interesting thing, is that, okay, so the question is what protection was used on audio CDs? And the big problem with that is that you had digital. They were copyable. I remember there was a big ruckus about the first home recording DVD or CD player. I think it was made by Philips, as it turns out. But there was no protection, none at all. Now, that mistake wasn't repeated for DVDs that recorded movies, but that was probably the big problem of lack of preparation for what could happen as the new CD technology was introduced.
Well, to be clear, the protection on the CD was the fact that 600 megabytes was too big to move around on a P32 modem. People thought there was an inconceivable amount of data to send anywhere. But, I mean, DVD had protection, but it was a 40-bit key with no renewability.
Yeah.
Which was hacked on a PC, like how many years after the DVD came out?
It wasn't that long, but at least there was an effort, and legally that turned out to be somewhat of a difference too. You know, the audio people or the music industry seemed as if they were deploying a technology that they didn't care, and that's not true of the movie industry.